Look around you. Right now. That wall, your hand, the air you're breathing. What if I told you that, at the most fundamental level, none of it is really there? What if everything you think of as solid, empty, near, or far is just a high-resolution illusion? A story being told by something much, much weirder? Because the deepest question in all of physics isn't about stars or atoms. It's this: what is space itself? And the answer isn't just mind-bending, it might change how you see everything, including the distance between you and the people you love. So let's do a thought experiment. It's the ultimate deep clean. We're going to strip the entire universe of every single object. Every star, every planet, every speck of dust. Poof. Gone. Every atom, every particle, every last echo of you and me. What's left behind? For most of human history, guided by the titan of physics, Isaac Newton, we had a beautiful, simple answer. We're left with the stage. An empty, invisible, three-dimensional grid. A cosmic coordinate system just waiting for actors. Newton called it absolute space. A fixed, eternal, and frankly, boring background that was the same everywhere, for everyone. It was the unmoving theater in which the drama of the cosmos unfolded. But then, a humble patent clerk in Bern, Switzerland, named Albert Einstein, came along and didn't just tear up the script, he burned the whole theater down. He gave us general relativity, and with it, a picture so elegant and profound it still feels like magic over a century later. He said space isn't a rigid stage. It's an active player in the cosmic drama. It's a dynamic, flexible fabric. And matter and energy are the actors that tell this fabric what to do. You've heard the analogy: a bowling ball on a trampoline. The ball's mass makes a dip in the fabric, and that dip is what we feel as gravity. But let's really dive into that, because the details are where the magic is. Imagine the trampoline is perfectly flat. That's space with no matter. Now place a heavy bowling ball, our sun, in the center. It creates a deep, sloping well. Now roll a little marble, say, the Earth, nearby. It doesn't get pulled to the sun by some mysterious invisible rope. No. It simply follows the straightest possible path through the curved fabric. From the marble's perspective, it's going in a straight line. But because the fabric itself is warped, that straight line becomes a circle. An orbit. The most crucial part people miss is this: the trampoline is the thing. It's not in space. The curving, stretching, and warping of the fabric is space. Matter tells space how to curve, and the curve of space tells matter how to move. This idea is not just a pretty thought. It's one of the most rigorously tested theories in history. For decades, it explained the weird wobble in Mercury's orbit that Newtonian physics couldn't account for. During a solar eclipse in 1919, astronomers saw the light from distant stars bend as it passed the sun, exactly as Einstein predicted, making him an overnight global celebrity. Your GPS works because the satellites high above Earth, where gravity is weaker, have clocks that tick slightly faster than ours on the ground, a direct consequence of time itself being part of this flexible fabric. We've measured the Shapiro delay, the extra time it takes for a radar signal to travel through the gravitational well of the sun. And most spectacularly, we have heard the fabric of space-time ringing. When two massive black holes spiral into each other a billion light-years away, they create ripples in the fabric, gravitational waves, that travel across the cosmos and physically stretch and squeeze our detectors here on Earth by a microscopic amount. We've directly observed the cosmic trampoline jiggling. So, case closed, right? Space is a smooth, continuous, dynamic fabric. The end. Not even close. Because at the exact same time Einstein was weaving his beautiful geometric tapestry, another revolution was brewing. One that painted the universe with completely different inks. And this new picture says that empty space is the most chaotic, violent, and crowded place in the entire cosmos. Welcome to quantum field theory. If general relativity is the elegant ballet of the cosmos, quantum field theory is the mosh pit. In this version of reality, the fundamental building blocks aren't little balls of matter. They're fields. Forget particles for a second and think about what a field is. A magnetic field, for instance. It's not a thing you can hold, but it's a real property of space. It has a value and a direction at every point. A quantum field is a souped-up version of that. Think of an infinite ocean that stretches across the entire universe. That's the electron field. Another, separate ocean for photons. Another for the Higgs field. Every particle you've ever heard of is just a little ripple, a tiny, localized vibration, an excitation in its own universal ocean. An electron is just a place where the electron sea is splashing a little. Now here's the kicker. The rulebook for these quantum oceans is the Heisenberg uncertainty principle. In simple terms, it says you can't know certain pairs of properties perfectly at the same time. For a quantum field, this means you can't know both its exact value and its rate of change simultaneously. The consequence? A quantum field can never, ever be perfectly still. It can never have a value of exactly zero everywhere. That would be a state of perfect knowledge, which the universe forbids. So even if you take all the ripples out, all the particles, the oceans themselves remain. And they are never, ever still. The quantum vacuum, what we think of as nothing, is actually fizzing and seething with energy. It's a storm of zero-point fluctuations. The irreducible, fundamental jitter of reality itself. These aren't virtual particles popping in and out of existence. That's a useful but misleading picture. It's the fields themselves, endlessly quivering. This isn't just philosophical mumbo-jumbo. We can prove it. It has real, measurable effects. Take two perfectly smooth, uncharged metal plates and bring them incredibly close together, microns apart, in a perfect vacuum. What happens? They get pushed together. By nothing. This is the Casimir effect. The quantum ocean of the electromagnetic field is fluctuating outside the plates at all possible wavelengths. But between the plates, it's like a tiny resonance chamber. Only very specific, short wavelengths can fit. This creates a pressure difference. There's more energetic jittering pushing from the outside than from the inside, and it physically shoves the plates together. Emptiness is physically pushing on things. Let that sink in. And it gets weirder. The Unruh effect, a wild prediction of quantum theory, says that if you accelerate through a perfect vacuum hard enough, you'll feel warmth. The empty space will literally heat up from your point of view, creating a bath of particles where there were none before, just because you're moving. It's the ultimate friction with nothing. Your very state of motion determines what particles you perceive as real. So now we have two beautiful, powerful, and completely contradictory pictures of space. Einstein gives us a smooth, elegant, geometric dance where space is a placid, gently curving sheet. Quantum mechanics gives us a chaotic, buzzing, energetic foam where even the void is a raging storm. For 100 years, the greatest minds in physics have been trying to make these two pictures agree. And they can't. It's the biggest unsolved mystery in science. And to solve it, we have to go smaller. Much, much, much smaller. So let's shrink. Forget your room, forget a dust mote, forget an atom. We're going all the way down. Down past the nucleus, through the quantum fields, to the absolute floor of reality. We're going to the Planck scale. Imagine you're looking at a high-resolution photograph. From a distance, it's a smooth, continuous image. But as you zoom in, you start to see the grain. Zoom in further, and you see the individual pixels. The Planck length, about 1.6 times 10 to the minus 35 meters, is the suspected pixel size of the universe. This number is so small it's almost meaningless. If you were to scale up an atom to be the size of the entire observable universe, the Planck length would be the height of a single tree. It's the scale where our current equations break, where gravity becomes as strong as the other forces, and where our ideas of smooth and continuous just stop making sense. It's the do not trust below mark on nature's ruler. So what do we find down there? Is Einstein's fabric smooth all the way down? Or is it made of discrete quantum pixels? Is it a calm pond, or is it a pot of water at a rolling boil, what legendary physicist John Wheeler called quantum foam, a seething chaos of tiny bubbles of spacetime, microscopic wormholes, and virtual black holes flickering in and out of existence faster than we can comprehend? This is where we hit the frontier. And on this frontier, three huge paradoxes are waiting for us. These are the clues that might finally solve the mystery of what space really is. Paradox 1, the smooth versus the chunky. As we said, Einstein's world is smooth. But a leading contender for a theory of quantum gravity, called loop quantum gravity, LQG, says the opposite. It predicts that space isn't continuous. It's built from finite, indivisible loops woven into a network. Imagine a cosmic chain mail. The state of space at any moment is described by a diagram called a spin network, where nodes represent tiny, discrete chunks of quantum volume, atoms of space, and the lines linking them represent quantized units of area. You can't have any area, you can only have specific, discrete amounts of it, determined by numbers called spins. It's as if the universe measures itself in clicks, not a steady sweep. And time? In LQG, time isn't a flowing river. It's the sequence of discrete moves that rearrange the network, like a cosmic game of chess. This evolving spin network is called a spin foam. If this is right, then the smooth space we experience is just a large-scale average. It's like looking at a fine mist. It appears continuous, but it's really made of countless tiny raindrops. Our reality is a clever illusion created by gargantuan numbers. Paradox 2, the nearby versus the connected. Normally, we think things influence each other locally. To affect something over there, you have to travel through all the points in between. But quantum mechanics has this ghost in the machine called entanglement. Einstein famously called it spooky action at a distance. You can link two particles so that they become one single quantum system, described by a single wave function, no matter how far apart they are. If you measure a property of one, say, its spin, you instantly know the spin of the other, even if it's on the other side of the galaxy. To be clear, no information travels between them faster than light. There's no signal. It's more profound than that. They were never truly separate to begin with. Their fates are correlated in a way that defies our classical intuition about space and distance. This spooky connection has led to one of the most radical and exciting ideas of the 21st century, it from qubit, or the idea that space-time is emergent from quantum information. The idea is that space, geometry, and distance might not be fundamental at all. Maybe they emerge from patterns of entanglement. Think of it like a cosmic social network. The more entangled two particles are, the closer they feel to each other in this deeper network. The less entangled, the farther they are. What we call distance is just a rough, macroscopic measure of the strength of these quantum connections. There's even a poetic and powerful shorthand for this idea, a conjecture called the R equals EPR. Proposed by Leonard Susskind and Juan Maldacena, it says that a wormhole, an Einstein-Rosen bridge, or ER, is the geometric picture of two entangled particles, an Einstein-Podolsky-Rosen pair, or EPR. The wormhole isn't a traversable tunnel for spaceships, but a profound hint that the geometry we feel as space might just be the bookbinding of these deep quantum correlations. Space is not the container of things, it's the web of relationships between them. Paradox 3, the problem of time. This one might be the biggest mind-bender of all. When you try to write down the master equation for the entire universe in quantum gravity, an equation called the Wheeler-DeWitt equation, something very strange and disturbing happens. The variable for time, t, just drops out. The equation is timeless. It doesn't describe a universe that evolves in time, it describes a static, frozen universe. A block universe where past, present, and future exist simultaneously and on equal footing. So where does our powerful, undeniable feeling of the flow of time come from? The idea, championed by physicists like Julian Barbour, is that time, like space, might be relational and emergent. It doesn't exist for the universe as a whole. It's an emergent property that arises when parts of the universe are measured relative to other parts. Clocks don't measure a universal ticking. A clock is just one physical system, gears turning, atoms oscillating, changing in relation to another physical system, the Earth rotating, you aging. Barbour imagines a timeless landscape he calls Platonia, containing every possible now, every possible configuration of the universe, all existing at once. What we experience as the flow of time is just our consciousness tracing a path through this landscape, from one now to the next, like a movie projector clicking through still frames. Our memories of the past aren't ghosts of a time that no longer exists, they are physical structures, or time capsules, that exist in the current now. The choreography creates the beat. If time is born from relationships, then maybe space is too. Maybe the stage itself is an illusion, and all that truly exists is the dance. Okay. That's a lot of wild ideas. Chunky space, geometry from entanglement, a timeless universe. This sounds like science fiction. How could we ever tell if any of this is actually true? How do we audit these claims? Science isn't just about cool ideas, it's about evidence. So let's be ruthless auditors. What does the data say? First, that buzzing vacuum we talked about. The Casimir effect is measured in labs every day. It's real. The vacuum is not empty. Claim audited, true. Second, the idea of grainy, pixelated spacetime. If space were chunky, it should affect light that travels a very long way. Imagine a high-energy gamma-ray photon and a low-energy radio photon leaving a distant galaxy at the same instant. If they are traveling through a pixelated medium, like marbles through a pile of sand, the high-energy photon might interact with the pixels slightly differently, causing it to be delayed by a tiny, tiny amount. After traveling for billions of years, that tiny delay should add up. We should see a smear, with different colors arriving at different times. So we look. We use telescopes like the Fermi Gamma Ray Space Telescope and neutrino detectors like IceCube at the South Pole to watch for photons and neutrinos from the most violent explosions in the universe, gamma ray bursts. And what do we see? Nothing. Across billions of light years, the particles arrive in a dead heat. This doesn't completely rule out pixelated space, but it puts an incredibly tight leash on the simplest models. If space is grainy, it is shockingly smooth. Claim audited, inconclusive, but leaning against simple models. Third, some theories, particularly the holographic principle, suggest that if our 3D space is an emergent hologram projected from a 2D surface, there should be a fundamental jitter, a holographic noise in spacetime. An experiment at Fermilab called the holometer was built specifically to look for this. It was essentially the world's most sensitive microphone, listening for a tiny, specific hiss in reality itself. After years of listening? Silence. No holographic noise was detected. Claim audited, no evidence yet. But here's the most exciting frontier experiment being designed right now. Can we make gravity itself create entanglement? The idea, proposed by scientists like Sagato Bose and others, is to take two microscopic diamonds, each about the size of a virus, and levitate them in a vacuum. Then, using quantum tricks, put each diamond into a superposition of being in two places at once. Now you have two tiny Schrödinger's cats, separated from each other. If they only interact through their mutual gravity, and after a while we find that their quantum states have become entangled with each other, it would be the smoking gun. It would prove that gravity itself must be quantum. Because only a quantum interaction can create quantum entanglement. These experiments are monumentally difficult, pushing the very limits of technology, but a clear result, yes or no, could be just a few years away. The mystery still stands, but we are actively, finally, putting it to the test. So let's step back from the frontier. What does all of this mean for us, right here, right now? If space really is emergent, if it's built from a deeper web of information and relationships, then here and there are not absolute facts. They're just convenient labels for how strongly things are connected. And on a human scale, that idea lands with a quiet, powerful thud. Think about loneliness and closeness. We use the language of space as a metaphor. We say we feel distant from someone. We talk about closing the distance. What if that's not a metaphor? What if those feelings are tapping into this deeper truth? Maybe distance is less about the miles between two bodies and more about the quality and bandwidth of the informational channel between two minds. A shared story, a vulnerable conversation, a burst of laughter, these things create coherent information exchange. They build a bridge. They literally, on some fundamental level, reduce the separation. We've all felt this. A late-night video call can collapse continents, making someone feel like they're right there in the room. While sitting in silence just a few feet away from someone can feel like staring across an infinite void. Networks create nearness. Isolation stretches distance. This reframes our entire technological world. Social media isn't just connecting people, it's reweaving the fabric of relational space. Remote work isn't just about convenience, it's a test of whether we can maintain informational closeness without physical proximity. Our digital lives are a grand experiment in the emergent geometry of human connection. So let's go back to where we started. Your room. Imagine the object's gone again. But this time, don't see an empty void. Don't see a blank canvas. Instead, see a shimmering, invisible pattern. A web of connections. The causal footprints of the light that just crossed the room. The ghostly correlations that tie every particle in your body to particles in a distant star. The infinite potential for future interactions, humming in the quantum fields. Maybe the universe is not a place that we are in. Maybe it's a pattern that we are. A verb, not a noun. An ever-changing story that information is telling about itself. Tonight, try this. Think of someone who is far away. Someone you miss. Send them a message. Not just a hey, but something real. A memory. A question. A hope. Something that could only come from you, to them. And just notice how the felt distance between you changes. Not in miles, but in meaning. Because if these wild ideas from the edge of physics are telling us anything, it's that the most real things in the universe aren't distances, but connections. What's one thing in your life that feels less solid, less certain after this? Let me know in the comments below. I read every one. And while you're thinking, I've put a video on the end screen that pulls on another thread of reality. Click it. You won't regret it. Subscribe for more audits of the universe. Because the map we have is not the territory. And the search for the real one is the greatest adventure of all.